Il y a plein de caméras sur le... Ouais, donc là, ah oui, parce que la caméra, elle fait elle filme plein de trucs. Et oui, donc il faudrait pouvoir faire au zoom lequel il prend, c'est ça.
Donc, moi, j'ai l'image avec des petits carrés, mais ça, c'est normal. La caméra, celle-là, elle fait 360 degrés.
Ouais.
Elle zoome en bas sur une personne. Et en haut, elle a le panoramique complet de toute la salle. Et quand il y a deux personnes, elle essaie de suivre la personne qui parle. Et quand il y a deux personnes qui parlent, elle split la truc en deux pour montrer les deux. Sauf que, bon, ça marche pas forcément très bien. Alors, là, tu vas t'écouter. Là, je vais rétablir l'autofocus. Ça, c'est YouTube. Donc, c'est pour ça que c'est décalé. Moi, j'arrive pas à me connecter à YouTube, de toute façon. Le navigateur, il ne veut pas. YouTube n'existe pas. Voilà.
D'accord. En tout cas, sur YouTube, on voit les différents banques de la caméra.
Oui. Je pense que je vais utiliser du RAM, parce que de toute façon, je ne sais pas si c'est utile, si on a décidé qu'on n'avait pas de caméra YouTube. Mais... Ah, bon, donc ça, c'est pas mal. Parce que ça montre. Qu'est-ce qui se passe si toi tu parles? Si toi tu parles, c'est cette caméra-là qui va le prendre.
D'accord.
Tu coupes ton micro.
Oui, j'ai coupé. Oui.
Donc, c'est OK parce que toi, tu partages ton écran,
Oui.
mais c'est avec cette caméra-là.
Okay.
Et donc, ça restera comme ça. Et quand les membres du jury parleront, la caméra se tournera vers l'autre.
Oui.
Et on pourra, tu vois, là, comme toi, là, on a tous les deux cette caméra. Non, mais tu vois la caméra?
Sur Google ou sur YouTube?
C'est les deux, c'est la même chose.
Oui, c'est la même chose. Oui, oui, d'accord, je vois la même. Et il y a la vue panoramique aussi.
Voilà. Ça, c'est pas mal. Éventuellement, je contrôlerai la caméra à la main si elle fait n'importe quoi pendant la soutenance, pour qu'elle zoome sur toi, et on la laissera faire ce qu'elle veut avec ses machins pour développer un petit morceau pendant une série de questions et de réponses.
Oui, très bien.
Non, mais c'est pas mal comme ça. Parce que pas la mettre juste tout près, mais un petit peu, genre, une table après celle du jury, et puis je pense que c'est pas mal. Bon, alors désolé, ça.
Pourquoi tu serais désolé?
Parce que j'ai essayé de faire marcher ce truc qui marchait particulièrement bien hier. On va nous méfier qu'aujourd'hui ça marcherait pas aussi.
Il n'est pas vendredi, c'est tout. C'est pas peut-être du lundi.
Non, mais c'est. Je sais pas, c'est mon port USB, mon bus USB qui est assez capricieux. Et là, elle a décidé que le système de mouvement va être déconnecté. Elle se connecte, et hop, au bout de 2 secondes, elle la déconnecte et elle réinitialise le bus et puis elle essaie. Et quand on fait ça, Zoom il se gèle à chaque fois. J'ai une image qui fait le monde. Bon. Ok, bon. Alors, écoute, du coup, en plus, comme je te dis, le son n'était pas mal hier. Je pense que ça reste ailleurs.
Et bien, c'est parti, mon kiki.
Alors. Bon, écoute, vas-y, continue.
Welcome to the defense of my thesis on static analysis of program portability by abstract interpretation. This work was performed as part of a cooperation between Sorbonne University and Airbus. A word on the role of software and the cost of bugs first. Modern societies tend to devote increasingly important roles to software. For instance, software controls the flight of aircraft, the brakes of cars, emergency systems of nuclear power plants, medical devices such as pacemakers, and inertial systems of rocket launchers. Such systems are called safety critical as bugs may have severe consequences, including the loss of human lives. In addition, software evolves over time, and software tends to be used much longer than anticipated at design time and in a much wider variety of environments. As a consequence, bugs can be introduced not only in initial development, but also in later versions, in which case we call this a regression. But bugs can also originate from running the software in an environment for which it was not suitably adapted, which we call a portability error. And this is concentrated on the two last cases of errors. We will use the glorified example of the Ariane 5 maiden flight that reused the software of Ariane 4 inertial systems, but run this software in the Ariane 5 different environments with larger accelerations, resulting in the inertial systems faulting and failing, and the flight, the rocket to self-destruct itself after 30 seconds of flight. So the direct cost of this bug is about $500 million. Indirect costs are probably larger. Software verification is mandatory for this type of safety-critical software. So we would like to verify software using program verification techniques. So what techniques can we use? We would like techniques to be automatic for efficiency. We would like techniques to be sound, meaning that all errors are detected. And ideally, we would also like techniques to be complete, meaning that all warnings actually point at a true error, no false positive, no false alarms. Unfortunately, Wright's theorem tells us that no such technique can exist. So we have to make compromises in most of us, do testing, because testing is automatic, and testing is complete, as testing can show the presence of bugs. But testing is also unsound, as testing cannot show the absence of bugs. Some people also do program proofs, which is a way to express and verify very precise properties of software. But this technique cannot be completely automated. As a consequence, it is quite hard to use on large complex software. In this thesis, we concentrate on another technique called static analysis, which is sound and automatic. It automatically infers runtime properties of computer programs, but it is also incomplete, as it emits false alarms, false positives. These three techniques are in use at Airbus in the avionics domain, where safety is paramount, and where software is pervasive. Indeed, aircraft functions have been transferred in the last decades from hardware to software. This is the first civil aircraft with no software, and this is the Airbus A350 flight deck with a lot of software. Avionics software are thus considered critical components of embedded systems. They have a major impact on safety. Think, for instance, about fly-by-wire control systems, and they're widely used in modern aircraft. They're thus liable to certification by third parties on behalf of authorities, and developers must follow the stringent rules on development and verification processes imposed by the applicable international standard. This standard tends to be biased towards traditional process-based assurance, relying on informal verification techniques, such as intellectual reviews and testing. These classical software are as follows. We derive high-level requirements, which is software specification. From system requirements, we refine it into a design composed of an architecture and low-level requirements. Then we write the code, and then we verify the compiled code against low-level requirements and against high-level requirements using testing. And then we re-verify every artifact that we have derived for accuracy and consistency by reviews, and we re-verify every artifact by reviews for conformance to upstream artifacts. So this results in a very heavy process, in a large verification effort. Unfortunately, this process, which has been in use for decades, does not scale well to the size and complexity of today's avionics software. Indeed, the size of avionics software has grown exponentially in the last decades, from a few million lines to a few 100 million lines of code. And the cost of software development tends to increase, and especially the cost of verification tends to blow up And in recent projects, we have observed verification costs being liable for 70% of the overall development costs. So to face this economical risk, Airbus have changed software processes. We have constructed more automated processes, and we do that by formalizing design artifacts more in order to automate verification. And the only sound way we have found to automate verification while preserving safety, which is paramount in our domain, is by leveraging formal verification. So we use static analysis by abstract interpretation on source and compiled codes, for instance, to prove the absence of runtime errors. We replace most unit tests with program proofs, and we do most such formal verification at source code level by leveraging the formally verified compiler. And this process has been shown to be cost effective. Now we will focus on abstract interpretation. So let us present the principles. The principle is in 3 steps. We first define the concrete collecting semantics of the program. That is to say, a mathematical model of the set of its possible environments, which can be constructed from the semantics of individual commands of the programming language. Then, in the second step, we define a specification, which is the subset of behaviors that you allow. And finally, we conduct a formal proof that the semantics meet the specification. And for this process to be efficient, we want to give computers to automate the proof. Here is an illustration of the semantics of a computer program. We have the same variable x that evolves over time. Let's say that x represents a set of values of program variables. So the program has a number of possible trajectories, and the set of all possible trajectories is precisely the complete semantics. The specification can mean that the semantics do not cross a forbidden zone. It's a safety property. And the formal proof is an inclusion test that the semantics meets the specification. Unfortunately, the concrete semantics is a non-computable object in general. So the way abstract interpretation sidesteps this computability issue is by deriving in a sound way an abstract semantics, which is a represented superset of behaviors with respect to the concrete semantics, and then try to prove that the abstract semantics fits in the specification. When this is the case, this entails correctness because the abstraction is sound. When using a static analyzer by abstract interpretation, you are likely to have some alarms. Alarms means that the abstract semantics does not fit in the specification. This can point at a real error, or this can be a false alarm due to incompleteness, due to the abstraction of the semantics being too coarse to prove correctness. As a consequence, static analysis tools tend to use a variety of abstract domains in a trade-off between cost and precision of the analysis. For instance, they use numerical abstract domains to approximate the set of values of program variables during concrete executions. Yeah, so you can use, for instance, the interval domain, which only records the minimum and maximum values of individual program variables. It is very cheap, but leads to imprecise analysis alone. On the other side of the spectrum, the polyhedral domain approximates soundly the set of linear relations across, between program variables, but comes with a very high cost. And some subsets of polyhedra, such as octagons, allow for rather precise analysis at a more reasonable cost. In this thesis, we leverage static analysis to apply it to 2 program equivalence problems: regression verification and portability verification. Regression verification, the objective of regression verification is to prove that a change in the program code will not add undesirable behaviors. The objective of portability verification is to prove that a change in the environment of the program will not add undesirable behaviors. For both problems, we derive static analysis that infer that 2 symmetric closed versions of the program compute equal outputs when run on equal inputs. In the case of regression verification, our patch analysis considers the program running in the same environment. In the case of portability analysis, we assume that both programs run in their respective environments. After this introduction, we will move on to patch analysis for numerical programs using the toy language. Then we will leverage this work to address patch analysis for C programs and related structural layout portability. And we will continue on the portability properties of C programs related to indiness and conclude. So let's get started with patch analysis. We start with the motivating example. This program here reads inputs into variables A and B, initializes a counter to value 1, then it increments a counter in the loop 8 times with value B, and then it outputs the value of the counter. That's program P1. Now we might want to change the code, and this is version P2, where we initialize the counter to 0 instead of 1, and output the counter plus 1 instead of the counter. Now we would like to prove equivalence of these two versions. So what we do is we prove they read equal inputs. So A1 is the value of variable A in program 1, A2 is the value of variable A in program 2, and similarly for B. So we assume they read equal inputs, and we want to prove they write equal outputs. So that R1 and R2 are equal. This can be done classically by comparing the input-output relationships of these programs and by deriving systematically local invariance of the programs. So here we have two similar, though not equal, loop invariance. And using this loop invariance, we can see that both programs have the same input-output relationships. As a consequence, we can prove equivalence using this method. However, this method cannot be easily automated, as it makes it necessary to infer arbitrarily expressive invariants, such as nonlinear invariants here, which are beyond polyhedra. So that would cost a very, very costly numerical abstraction. So we go for another option. Instead of analyzing programs separately and comparing input-output relationships, we want to analyze them jointly. And to do that, we first merge their syntactic structures by creating a double program. This is a joint syntactic representation of two versions of the program. Here, the double program, the meaning is both program versions read input into A and B, and then program 1 assigns 1 to C, and program 2 assigns 0 to C. This double program is derived using edit-distant algorithms implemented through dynamic programming, and it can be used to find back versions 1 and 2 using projection operators, taking the left-hand side or the right-hand side of the parallel symbols here. The parallel symbols are the distinctive trait of this double program language to express syntactic difference. And then we analyze the double program with a dedicated double program semantics, and it turns out that we can prove correctness using less expressive invariants, here linear invariants, relating to loop counters. Now, let us present this double program semantics we use. Well, we simply lift simple program semantics. Simple programs, P1 and P2, have simple states which are standard stores from variable to values. Their semantics are standard input-output relations on states. And double programs have double states, which are pairs of simple states. State of program 1, state of program 2. And the semantics of double statements are relations over double states. The semantics of the composition of two syntactically different statements simply pairs the semantics of individual statements computed with simple statement semantics. This construct is used to define the semantics of assignments. The semantics of inputs and outputs are as follows. Both program versions write the same value into the input variable v, and the semantics of output checks that both programs agree on the value of variable v, otherwise an alarm is raised. And then, moving away from atomic statements to compound statements, the semantics of compound statements is defined by structural induction of the syntax of double programs. For instance, the semantics of the sequential composition is the composition of semantic functions. The case of if statement is specific. It relies on the F filter here to distinguish between 4 cases. In the 2 first cases, the 2 program versions agree on the value of the test expression, and they're actually standard. In the 2 last cases, which are called unstable cases, they disagree on the value of the test expression. And for this case here, for instance, we compose the left version of the then branch and the right version of the F branch, filtered by the condition or the negation of the condition. And this is the dual case. Intuitively here, this means that the first program version executes the then branch and the second program version executes the else branch. Now, the case of while statement is defined using a least fixed point classically, and the definition of the operator is similar to the definition of if statements. This is the loop invariant here. It says that as long as both program versions, as long as the loop condition is true for both program versions jointly execute the loop body. But as soon as it turns out to be false for one of the program versions, well, this program version waits for the other one to complete. The other program version continues to run its version of the loop body. And then both programs meet again after the loop. Now, let's move away from the semantics and come back a little bit to double program construction. In the less trivial case, this is a simplification of a real patch of the group core activities. These 2 versions are syntactically quite different, and they feature quite different control structures. What we do is we first merge identical statements here by leveraging standard least common subsequence computations here. Then we align similar control structures. Here we only align 2 assignments because these control structures are very different. But we also allow ourselves some simple syntactic program transformations, such as this if true here, which allows to again align similar control structures. And this way, we derive this double program here that has merged the control structures to benefit from the induction of the syntax provided by our semantics. And it turns out that we put equivalence to the 2 program versions here using only linear invariance. Now, we have presented patch analysis on the toy language, but let us move away from the toy language to our real target, which is C, and more precisely, low-level C. So we will present patch analysis and also implicitly structural layout portability, as patching or changes in ABIs can change the positions of scalar values in memory. Okay, this is a C program. Let us forget a while about patches. It has a data structure here. It inputs, it reads input into field B. It has a pointer. It does heterogeneous pointer cast and pointer arithmetics. And at the end of the execution, the pointer points to the last byte of field B, which is the 2-byte field inside the 4-byte structure S. Now, at the most concrete level, this program holds values for individual bytes. Yet, the program has multi-byte access to memory, and we would like to infer numerical invariance. Hence the need for scalar cells, which are synthetic scalar variables that hold values for the memory references in the program. In addition, we see that here, this low-level C program abuses the pointer here to get byte-level access to the encoding of the scalar value. As a consequence, cells overlap. So we need a memory model to handle some of these kinds of programs, and this memory model has been defined by Millet in the cell abstract domain. Memory is viewed as a dynamic collection of cells, which are holding values for the memory dereferences discovered during the analysis. More precisely, cells are tuples with a base variable, an offset, and a scalar type. The analysis can be run with any numerical domain using one dimension a cell. Here are the cells synthesized in this example. There is a blue cell here for the byte of field B. There is a pink cell for the pointer derivative here, and there is a 4-byte cell for the pointer itself. In addition, the memory domain identifies numerical constraints between cells, which are called cell constraints. And, for instance, here, assuming little endian, it tells that the pink cell is the high order byte of the blue cell. This constraint can be represented more or less precisely in the numerical abstraction depending on the numerical domain we use. Now, let us use this cell memory model to do patch analysis on C programs. So we introduce a patch on our program here, we remove field A, and we change the pointer arithmetic so that both program versions point to the last byte of B at the end of the program. Here is the representation of the memory of the left program, the memory of the right program. And let us show the invariance, blue cell, pink cell. The semantics of inputs guarantees that the blue cells are equal. And then we would like to prove that the pink cells are also equal. Well, all we have to do that is use the cell constraints from the memory domain. As a consequence,
Ah, tu as laissé le clé.
Bon, j'enlève la pause. We can indeed prove equality from the program invariance and cell constraints that we have inferred, but this requires the numerical abstraction to precisely represent these equalities here, and this would require an expressive domain, probably more expressive than polyhedra. So this would be quite costly. But we notice that we are often only trying to infer equalities, and equalities between matching cells into the two memories. This is not a surprise. We expect that in most of the time, the multi-byte scalars hold equal values in two memories with only local deviations. So we optimize our memory model for this common case, and we do it by sharing the representation of cells in memory environments. We used a single representation for two cells coming from different program versions and holding equal values, which we call a B cell. A B cell is thus either a single cell coming from the memory of program 1 or program 2, or a pair of such cells holding equal values, which we call a shared B cell. Now, when we move from cells to B cells, we first merge the representation of memories here, and then we analyze the program. When reading inputs, we know that both program versions write the same value to field B, so we can synthesize a shared B cell for the blue cell. And then when dereferencing points of P here, we would like to prove equality of between the pink cells. So the way it is done is by trying to synthesize a shared B cell as a proof of equality. And to do that, the memory abstract domain matches the memory environment against a number of patterns, such as the following. It first looks in the memory environment whether a B cell would already be available. It's not the case here. It could also query the numerical domain for equality. Yet, as we said previously, that would be extremely costly in this case, so we don't do that. Instead, we look at other patterns, such as this one. Can be found in the environment two cells, x1 and x2, that are equal, and such that C1 prime, it has some offset inside x1, and similarly for C2 prime. Well, the answer is yes. We have C1 and C2 that match at offset 1. As a consequence, we can use this pattern to synthesize a shared B cell. And we synthesize the shared B cell as a proof of equality only by pattern matching. We can additionally inform the numerical domain about this relation, but it does not matter if it is represented imprecisely. We already have the symbolic representation of equality. Now, we have implemented this analysis on top of the MOXA platform, which allows for modular development of precise static analysis for multiple languages and multiple properties. Our prototype is a few thousand lines of vocabulary, half of which for the B-cell-based memory abstraction, a third of which for double program construction, and the rest for double program iterators and utilities. Our prototype leveraged much more lines of the MOXA platform itself, with parsers and utilities, a large common framework, and iterators and numerical domains for generic to all languages or specific for C. This is not patch analysis. This is the architecture of a static analysis of C programs with MOXA. It has a number of iterators for the statements of C and universal statements such as while loops. It has an abstract domain composed of a memory domain and a numerical abstraction with standard numerical domains such as intervals and polyhedra. Now, to do patch analysis with cells, we simply add double program iterators, and we lift the memory domain, the cell-based memory domain, using this patch counter here to the double memory. And that's it. But now, if you want the B-cell domain, well, we simply replace the composition of the patch functor and the cell abstract domain with the B-cell abstract domain. And that's it. Now, we have compared our work with related works, such as the modif tool here, based on symbolic execution, the rep tool, based on deductive methods, DCM scores that leverage abstract interpretation. We evaluated first on synthetic benchmarks from related work, or simplified benchmarks from related work. All benchmarks here are synthetic, except the three last ones, which are simplified versions of real patches of the GNU core utilities. We analyzed these benchmarks with our two memory models, with cells and with B cells, and we analyzed them with three numerical abstractions: polyhedra, octagons, and intervals. We don't display intervals in the case of the cell abstraction because it yields no conclusive analysis. We can see that we analyze very precisely the examples from the related work, usually much faster, and sometimes with one order of magnitude faster or more, such as here, or here, or here. When using the B-cell-based abstraction, we get similar results with polyhedra, but we get better results with less expressive domains, such as octagons, and we can even have conclusive analysis using the non-relational interval domain, which leads to precise analysis that are very efficient with respect to the related works. Now, we have also evaluated our work on the real patches from core utils and Linux. This is from core utils, and this is from Linux. The core util patches change the code, the algorithm, while Linux patches mainly change data structures. We can see that the cell-based and B-cell-based abstraction have similar results with polyhedra, but B-cell-based abstraction allows for much more scalable analysis, as it works most of the time with the interval domain, which allows to scale to medium-sized programs in a very short time, whereas the polyhedra abstraction is very costly. Now, note that the three first examples are the real versions of the simplified benchmarks from related work. And we can see that we have analyzed the real code with the same speed as the simplified code. Now, let us move away from patch analysis and present our Indian portability analysis. A word on Indian first. There's no consensus on the representation of a multi-byte scalar value in computer memory. Little Indian systems store the least significant byte at the lowest address, while big Indian systems do the opposite. Little Indians include Intel processors, while big Indians include internet protocols in legacy or embedded processors such as SPARC or PowerPC. Note that such a conflict might even trigger religious wars, such as the one Lilliput witnessed when traveling to the island of Lilliput, where he met little Indians who insisted that eggs should be broken at the little end, while big Indians wanted to do the opposite. Now, Indianness is an important source of portability errors, especially in the case of low-level C programs. Indeed, the C standards that leave the precise encoding of scalars partly unspecified. As a consequence, running the same code on two platforms with opposite Indianness can lead to different behaviors. And porting a program originally written for one platform to a platform with opposite Indianness can be quite challenging. Let us illustrate this on an example. Here we have a small example originally written for a big Indian platform. It reads a 2-byte integer into variable x. Then it copies x to y, and then it reads y using the big Indian convention. The value is 1. Now, what happens if we run the same program on the little Indian platform? Well, we get the same bytes, but when reading y with the little Indian convention, we get a different value. Now, if we would like the same value, we have to change the code by replacing the assignment here with a byte swap. So we read x, byte swap x into y, and then read y using the little Indian convention, we get the same value as with the big Indian program. Now, if we use conditional inclusion directives to merge the two versions of the program, we get a so-called Indian portable program, which ensures that both program versions read the same value for y. Note that there are other ways to byte swap x into y, such as bitwise arithmetics. So the program is called Indian portable. If two Indian specific versions thereof compute equal outputs when run on equal inputs on their respective platforms, we present a static analysis to infer Indian portability of large real-world C programs. As we have noticed in the example, the semantics of memory reads and writes depends on the ABI, and more precisely here on the Indianness. So we must parameterize the semantics of C program with their Indianness. And in particular, we must extend the memory model to reflect the fact that the value for multi-byte cells actually depends on the Indianness. And we do this by writing into the definition of cells their Indianness encoding. A cell can be encoded in little or big Indian. Now we have simple programs which are little Indian or big Indian programs that their states are environment over cells, and their semantics is parameterized with their Indianness. Now the double program semantics is a pair, has double states, which are pairs of states, the little Indian state and the big Indian state. And then semantics are input-output relations on these double states. The transfer functions are mostly unchanged with respect to path analysis. The only slight difference when composing two syntactically different versions is that each program version is interpreted with the Indianness of its platform by the simple program semantics. Otherwise, it's the same. Now, let us analyze the motivating example with cells. We read bytes into X, which creates these 1-byte cells, and we call equalities in numerical abstraction. Then we byte swap X into Y, which creates 1-byte cells into Y and equalities. Then the big Indian version of the program reads X from the values of overlapping 1-byte cells here, and then it assigns X to Y, and then both program versions read Y. As we already have YB, we synthesize YL from the values of overlapping 1-byte cells, and then we query the numerical abstraction for equality. Equality can indeed be proved from the program invariance and cell constraints inferred. But again, this would require an explicit domain to fully Hydra, and this is not an option, as we plan to scale to large programs. But again, we noticed we want to infer mostly equalities from matching bytes on the two memories. So we use the the B cell trick again. We optimize the memory model for the common case by sharing the representation of equal cells in the memory abstraction. We use again shared B cells, which are pairs of cells coming from different program versions with equal values, and they can represent equalities or equalities modulo byte swapping, depending on the the indigenous encoding of the members of the shared B cell. Now, recall the analysis with cells. We had the little Indian memory here, the big Indian memory here, and a lot of pressure on the numerical domain. Now, when moving from cells to B cells, we have merged the representation with memory, and we have much less pressure on the numerical domain. And when reading Y, we do not try to synthesize YL immediately. Instead, we try just a shared B cell synthesis. By matching the memory against a number of patterns, such as this one, can we find in the memory environment a cell C that would be equal to both YL and YB? Well, XB is a candidate because we have this equality here. And then is XB equal to YL? Well, we just have to look at the overlapping one-byte cells, and as they have opposite indigenous encodings, we query exactly for these inequalities here. So the B cell synthesis succeeds. And this success is due to abstract pattern matching and three simple equalities which can be easily inferred using a symbolic propagation or a full equality domain. Recall that Indian portable programs not only use pointer casts, they also use bitwise arithmetics. Well, an example here of this idiom. This program reads a byte into Y, then the little program stores the Y at the low order bytes of the 2-byte word X, and it stores FF at the high order bytes. And the big Indian program does the opposite. Well, now we would like to prove that both program versions construct the same 2-byte word. Well, again, we have complex linear invariants. But we handle this in a symbolic way by using the bit slice numerical domain inspired by it's a domain based on symbolic predicates that associates symbolic predicate values to individual cells, and it is actually inspired by previous work on predicate domains and symbolic constant propagation. And here it infers exactly what we said in the little Indian memory. The low order byte of X is the B cell YL of B, and the high order byte of X is 255, and it's the opposite in the big Indian memory. So with symbolic reasoning, we can easily infer equality here and synthesize shared B cell. Now we have implemented this Indian portability analysis on top of our patch analysis based on B cells by updating the B cell memory domain, by adding the bit size predicate domain. When moving from patch analysis to Indian portability analysis, well, we have exactly the same architecture. We only add here a reduced product between C machine numbers and bit slices. We have experimented our work on open source and industrial software. We analyze open source software projects available on GitHub with multiple patches due to Indian portability bugs. We analyze small slices thereof using our specification primitives. We are able to find all reported bugs on GitHub, and we're also able to prove Indian portability without false alarms where applicable. We also analyze two modules of an industrial application. It's a prototype avionics application developed at Airbus. This application is designed to run on the big Indian platform. Nonetheless, the two modules here, A and S, are designed to be portable to Little Indian, as they are also used as part of the simulator that runs on Little Indian platform. These are two large code bases. This is 1 million lines of code, and we analyze them quite precisely with no false alarms. All the findings we have had at some point have been incorporated into the development cycles because we have been working in tight cooperation with the avionics development teams and the simulation integration team. And as a consequence, the simulation team were faced with zero engineering issue when integrating module A into that simulator for the first time. Let us conclude. We have developed methods for the analysis of software patches and for portability analysis for engineers and for structure layout portability. Our main contributions are a double program semantics, memory domain based on B cells, numerical domains, and an implementation with experimentation. Our double program semantics allows to express the behavior of two versions of the program at the same time. It allows a joint analysis by induction of the syntax of a so-called double program. We give a heuristic algorithm for constructing a double program from a pair of program versions. We also discussed the support for unbounded input streams in the manuscript that allows program versions to desynchronize when reading inputs. The B-cell based memory domain is able to infer and represent symbolically important relations between the bytes of the two memories, and this allows some scalable patch analysis, especially patching of data structures, and scalable portability analysis. We have also developed two numerical domains with near linear cost. The bit-size domain represents relations between the individual bytes of of variables in the two versions, and the data domain discussed in the manuscript counts the differences between variables in the two program versions. Our prototype on top of MapSci is able to successfully analyze small slices of open source software and large real-world avionics software. For future work, we first plan to industrialize this analysis. We would like to use our Indian portability analysis as a means to support avionics certification objectives related to simulation fidelity. We also hope to use our patch analysis to support partially automate impact analysis in product line architectures. We could also extend our approach to portability analysis to further ABI-related portability properties, such as portability across platforms which feature different word sizes or different data models. We could address the pitfalls of porting from x86 or PowerPC to ARM. We could support the porting of applications between two OSs with two versions of an OS with different state types. We could help prepare 32-bit POSIX-based systems for the year 2038 problem, where time counters will overflow. And we could also look at different types of portability properties, such as what happens when we change the range of inputs, such as in the case of the Ariane 5 accident. Note that we have focused so far on proving equivalences, while other authors also characterize thematic differences. Well, we could do the same by extending our analysis. We could infer semantic differences between product versions. We could try to evaluate the cost of the patch in terms of loop iterations, for instance. And we could maybe define and infer an improvement property that proves that the patch only rules out undesirable behaviors. To finish, I will mention that our double program semantics is able to express hyperproperties. When composing twice the same version of a program in a double program semantics, it actually compares sets of execution of the same program. It can thus express two safety properties, which are informally defined as properties that can be disproved by a pair of terminating executions. So we have successfully experimented proving some secrecy and non-interference properties on small, simple benchmarks from the related works, and we might be interested in trying to look at further properties and larger, more complex programs. So thank you for your attention, and I'd be happy to take your questions.
Ok, bon, on a mis 45 minutes, donc c'était non, c'était bien. Quelques petites remarques.
Ouais.
J'aimerais vraiment retravailler quand même l'indianness de l'exemple, etc. Enfin, la manière dont tu présentes les choses.
Tu trouves que je l'ai retravaillé?
L'indianness.
Oui.
Ouais. Ça va un peu changer.
Ouais, peut-être un peu, je ne me rends pas trop compte. C'est pas forcément très simple.
Bon, alors du coup, Non, c'était bien. Peut-être que l'introduction est assez longue et à un moment, tu as introduit le but. Le but de la thèse. Ça pourrait être pas mal de faire une pause un peu plus longue à ce moment-là.
D'accord. Avant le go, avant le go.
Ouais. Peut-être d'arrêter le streaming sur YouTube.
Oui.
Ça marche, ça a l'air de marcher. Moi, je vais pas vérifier ici. Ça a l'air bien.